Hi, I'm Kenny Jones, and I'll be presenting the Neurally Guided Shape Parser, a method for 3D shape segmentation that assigns grammar-based labels to 3D shape regions through approximate inference. Segmenting 3D data into semantically meaningful decompositions is an important and well-studied problem within the field of computer vision. The typical problem statement for this task assumes as input a 3D shape or scene that can be represented in a number of ways, such as by a mesh or a point cloud. The goal is then to assign a semantic label to shape atoms, the lowest level geometric entity in the input representation. The ability to semantically segment 3D shapes is important for numerous applications, such as reverse engineering the part structures of an object to support editing and manipulation, producing training data for structure-aware shape generative models, or helping autonomous agents understand how to interact with objects in their environment. These applications often demand that the parts detected be fine-grained and hierarchically organized, but producing such segmentations has proved a challenging task. Recent work on 3D shape semantic segmentation has mainly focused on end-to-end approaches that operate on shape atoms. These methods achieve impressive performance on many tasks, but often do not transfer well to domains with fine-grained label sets or when access to labeled data is limited. Our method, the Neurally Guided Shape Parser, attempts to address these limitations by reasoning over shape regions instead of shape atoms. NGSP consumes a 3D shape as input that has been decomposed into a set of regions. Its goal is to find an assignment of labels to each input region that maximizes a learned likelihood function. As it's too expensive to exhaustively consider every possible label assignment under this likelihood, NGSP employs a neural guide network to propose high probability assignments. We find that compared with end-to-end neural approaches that learn to label shape atoms, NGSP performs better on fine-grained semantic segmentation tasks, even when access to labeled data is limited. NGSP's likelihood function is composed of learn modules that reason over either properties of the semantic labels of the grammar or properties of groups of regions implied by a given label assignment. For each label in the grammar, the semantic label likelihood term reasons about different properties of shape regions that were assigned to that label. The geometry likelihood term aims to capture typical geometric properties. The layout likelihood term aims to capture typical spatial relationships between a label's children. The region group likelihood term reasons about properties of region groups implicitly formed when a labeling is assigned to an input shape. The region network reasons over two properties of each group of regions created by an assignment. What is the best label for the group, and what percentage of area within the group belongs to that label. To guide the search towards high probability label assignments, we use a guide network that learns to locally approximate the posterior by independently predicting the probability of each possible label for each region. At inference time, NGSP creates a set of proposals by using the guide network to import and sample the top k label assignments to the input shape. Each proposal is then evaluated under the full likelihood, and NGSP selects the highest probability assignment within this set. We evaluate NGSP's ability to assign fine-grained semantic labels to regions of 3D shapes. Our experiments use CAD manufactured objects from the PartNet dataset. As input, we oversegment each shape using the mesh components for each part instance in PartNet. We compare NGSP against related methods that use regions to aggregate point predictions, incorporate regions into self-supervised training objectives, or assign labels to regions in alternative search-based formulations. We find that NGSP produces fine-grained label assignments that are more coherent and better reflect the ground truth labels compared with alternative methods. Quantitatively, using semantic mean intersection over union as our evaluation metric, NGSP outperforms the comparison methods by a significant margin when labeled data is plentiful. Even when access to labeled data is limited, NGSP outperforms the next best alternatives. In fact, NGSP's performance with 10% of the labeled data outperforms any comparison method that has access to all labeled data by almost 10 absolute percentage points. As NGSP requires a region decomposition as input, it can't be directly applied to some types of unstructured data without the help of auxiliary methods. We evaluate NGSP against alternative region labeling methods over unstructured input data, with regions created by an ACD procedure where only 10 labeled shapes are provided. Within this paradigm, NGSP outperforms other approaches that learn to label ACD-generated regions or ignore regions and label shape atoms directly. NGSP can be applied to in-the-wild CAD shapes found from online repositories, as region decompositions are often created as a byproduct of modeling procedures. Using regions sourced from connected components of ShapeNet meshes, we asked participants in a perceptual study to compare semantic segmentations produced by NGSP to those produced by alternative methods. For all conditions, we found that participants had a significant preference for the part labelings generated by NGSP. Please find our full paper, code, and data at our project page. Thank you for listening.